The first speaker will be Han.
Yeah, I think you need it.
Oh, is it Cal?
All right.
Cal, is that your phone?
Reminder you have topic.
No. You can help me to answer that. You have a better answer than me. All right, so good afternoon, everyone. So I was usually not put on the first speaker, but so for this particular reason, I put on the first. So not too bad. So it's really nice to be back again to the our annual theory meeting. So this is a very beautiful campuses. So this is Pittsburgh. Here is our National Tsinghua, and in particular, this is the fall colors. It's very nice. So I'm going to discuss some recent work I did with some collaborators. So as we know that LSC is going to continue to dominate our high energy frontier for the next at least 10 to 15 years. Now, of course, we have so many interesting questions to ask in the hope that the LSC will be able to shed light on. So today I want to make this connection with a different aspect. So this is about the neutrino physics. And in particular, about the neutrino physics, not within the standard model, in the hope to find some other new physics aspect to understand neutrino physics to a better level. Okay. So neutrinos are very important, as we know that everything from the postulation that the existence by Pauli, the existence for neutrinos, and then from the theoretical formulation for these the neutrino interactions. So here is, of course, our standard model description. However, these come back all the way similar to the Fermi's original formulation. So this is Fermi's Fermi constant and neutrino and the sector here. So of course, in the standard model, we also have the neutral current. This is the charge current. In the standard model, it's purely left-handed, and now we have 3 generations. Now it has so many important physics aspects for us to learn. And not only that the neutrino particle was first postulated in this interaction, but also this scale really tells you and the relevant electric physics that in fact in our standard model it's really given by the new particle, the weakly coupled particle W mass, and that's it. And then here is the neutrino sector equivalent to the very well measured the quark sector CKN. Okay. Then here we have this the mass mixing between the mass eigenstates and the interaction eigenstates, and hopefully neutrino sector will have some similar features that we can continue to learn from that. Okay. Now, of course, above the electric scale or near the electric scale, and this low energy approximation is invalid, we have to include the propagating fields. So that's how we introduce the direct couplings to the gate particles, the W and the Z's. So that's within the standard model. So that's the picture. However, even as successful as the standard model is, neutrinos remain to be most elusive. Not only the interactions are very weak, but also the properties. So far, when we think about neutrino physics, it's only needed for these Fermi interaction. It's only needed for these left-handed. There's no need for any right-hand neutrinos whatsoever. However, the new measurements tell us that neutrinos are massive. Then we need to extend the simplest picture. So that's why I said neutrinos remain to be most elusive. Okay. So we don't know whether there's a right-handed counterpart. We actually don't exactly know, but in particular, Gauram and those people pioneered the left-right symmetric theory, and we need to introduce the partners, right-handed partners, which is very appealing, but we still don't know whether those things are correct in nature. So that's an important thing. And we still don't know the neutrino mass is simply the Dirac-like, as what we described here from the Yukawa sector, or actually the neutrino will have this the only possibility to have this additional mass term. And maybe neutrino will help us for this leptogenesis and baryogenesis and so on and so forth. And the neutrino mass hierarchy we still need to measure better to understand, in the hope to understand the underlying dynamics. And maybe neutrino sector will provide sufficient CP validations for the baryogenesis and so on and so forth. It is also likely the neutrino sector may well be the next discovery beyond standard model, with so many hints, so many possible indications that we need to go beyond standard model. So today I want to discuss along this line to introduce another a very modest generalization. We call this non-standard neutrino interactions. So usually it's written as NSI. It's getting very common and very popular to study the generic properties beyond the standard model nature. So this is what I want to address in today's talk. So I have two topics along this line. So based on the two recent papers here, with some of this is my student, and Danny Moffat here was my former student. With some collaborators here, two papers appeared at the end of I think in August. In fact, in October. So one of them is the standard discussion about this non-standard interaction in connection with the neutrino oscillation measurements. In particular, the recent experiment, coherent experiment. So it's putting onto the very stringent bounds on the neutrino interaction already. So my question is that suppose we have this formulation to study the non-standard neutrino interaction, whether we have other places from observation viewpoint. In particular, for my personal interest, I want to see whether LSC can help to probe the similar interactions from the different aspects, from different angles. Similarly, we want to introduce another type of non-standard interactions with one particular scalar. So this is also interesting in the sense, and we have these treatable mechanisms to generate the neutrino masses. We usually call it type 1, type 2, type 3. It's kind of elegant formulations. We're trying hard to see which one is being really realized in nature by experiments. Now I want to go beyond it to see the non-standard interaction, to say that what else, the other observational aspects from along this line, we're able to test or not. And once again, in connection with Alex. So basically, the whole theme for today, just like the title said, I'm thinking about non-standard neutrino interactions, modest modification, modest introduction to the additional operators, and see what LSC, the other high energy experiment, can tell us. So that's the two papers. So first of all, this is the standard non-standard interactions. It's a non-standard neutrino interactions. This is left-handed. We don't need to introduce red-handed neutrino state yet, but because of measure effect, because of the interactions, and it's likely to go with the off-diagonal. This actually is original Wolfenstein parameterization. This is really the original, the MSW, the W Lagrangian. Wolfenstein wrote this down even as early as late the 70s, the 78. So that was the effective operator. So this is the standard parameterization called non-standard interactions. So the quark sector can be arbitrary with the different flavors, and also neutrino sector could have off-diagonal terms, and the parameters will be this epsilon with the different flavor indices, and also the possible coupling to different generations of quarks. So this is explicit form. So when you write down explicit form, you see that it has been deliberately normalized to the weak interaction coupling constant, the G Fermi. It doesn't have to be. If the new interaction exists, it may not be the W mass to suppress the overall. It may be a new interaction, lambda or something, but it's a convenient normalization. So the parameters, unknown parameters, could be in any size, the alphas, the epsilons, these. If you think this is due to a new neutral heavy Z particle interaction, then this coefficient epsilons will be similar to this the interaction strength, and renormalized with the electric scale to cancel the W mass and suppressed by the new scale. So these will be the typical size you are expecting for these new interactions. So this is the scaling effect. Okay. So first, the question I asked in the beginning, how we can go beyond these simple neutrino oscillation measurements, like the MSW effect, into the high energy regime with other experiments like LSC. But in order to do that, we need to have some kind of a semi-UV complete description, because you need to have proper propagator to apply to a higher energy region. So that's what we want to do first. We want to do a simple UV completion. The simplest possible UV completion you can think of would be just a Z prime, similar to a Z prime. But of course, talking about UV completion, the Z prime cannot be totally arbitrary. You need to have the anomaly free and these kind of simple requirements. So this is a simple formulation with a what is that? Ah. Ah.
Don't do anything.
We connect.
You connect? Yeah, very strange. It's similar to Sorry about that. I did not know what happened. So as we said, neutrinos are indeed weird. So let's continue on about the neutrino issues here. So let's try to see. Okay, let's just continue on. So let's have one simplest UV completion model. We introduced additional spin 1 particle called the Z prime. It has these anomaly-free coupling. These are the anomaly-free conditions. And for our simple choices, we want to make the life very simple to see the representative features. So we want to, the electron coupling is highly constrained from existing measurements, in particular from the low energy beam dump experiment and so on and so forth. So we just don't want to consider electron flavor because of the rather strong constraints. So the muons and taus are very loose. So we would select the 3 representative cases here. So this one to choose the charge, special new hypercharges to be same, and so you can avoid the significant flavor change in neutral current in the quark sector. So this is the quark sector region. And the lepton sector, we choose 3 cases. Case 1 is the muon flavor dominant. The other flavors are not important. The last one is the tau lepton dominant. The other flavors not important. The third case, the second case in between, is shared by the muon and tau. So those are 3 cases we want to demonstrate from these neutrino oscillation measurements, and also generalize beyond the neutrino oscillation to see the ellipse. So that's the simplest parameterization we want to do. So then we come back to the Wolfenstein parameterization for this the measure effect. And so we can impose the current measurements. The current measurements are from the global fitting. So we have global fit for this neutrino oscillation data. And so those are the current data, and consistent with some recent literature. So this is the recent literature, but very similar to what the numbers we obtained here. And those are the future. So those are from the future expectation for this the bound for this the couplings. You can see those are the effective couplings, something like from percentage level to order of 1. So those are the typical size where we're going to probe for these. So those are the kind of input parameter ranges from the current data, and then we will calculate these from our given theory. For our given theory, we're able to calculate these things by propagating this Z prime in the exact way. We don't make an approximation. But at a low energy, for neutrino oscillation data here, even we start from a few MeV, and then this is also very low energy already. And even for MeV range and the low energy measurement here, the effective parameterization is valid already. We can calculate this for a given theory. We use our given theory, the mass and parameter as the mass and coupling as parameters. only two parameters, mass and copy. So that's why I'm going to compare with the current low energy measurements from neutrino sector and the possible probe at the LHC. Okay, then we can calculate. So the other, beyond these simple neutrino oscillation measurements, we include the most recent, the coherent experiment. The coherent experiment usually is named by the called sevens. This is read as a sevens. The sevens is a generic name for coherent coherent elastic neutrino non-standard neutrino scattering. Okay. So here is the coherent neutrino scattering at the low energy, and coherent, the capital coherent is one particular name for the experiment. That is only experiment exists in Oak Ridge, so it's in the oscillation neutron source, and to do the low energy neutrino elastic scattering, so that you have the coherent enhancement over the number of nucleons squared. So that's a very interesting and cute experiment. It so turned out that this experiment is very sensitive to the non-standard interaction already. So we want to take that into account. So this is the formalism from the experimental side. Here is the detector behavior, the nuclear mass and the total mass, and this is the detector feature. Here is the probability density function, also given by the experiment. Given it's by the detector. The detector has a particular feature. Those are given by the experimental conditions. But here, this is our theory. This is our standard model decay spectrum. So typically, so they in their experimental environment, they have the stopped pions, and let the pions decay pretty much at the rest. So so here you know this monochromatic neutrino spectrum is calculated within our simple tree level diagram. And then this muon will subsequently decay to other anti-muon neutrino and electron neutrino. So those spectrum can be easily calculable within the standard model. You fill this in and use the experimental things. Then, of course, once you fill that in, we can use our theory. Our theory has this Z prime contribution to different nucleons, and given by these epsilons. We calculate epsilons according to our theory. So now we are able to make a prediction beyond standard model, including our particular Z prime model. So then finally we want to compare with LHC. When we want to compare with LHC, you look for the final stage. So this Z prime coupled to both neutrino and any charge lepton. So this pretty much is the generic feature. Generic feature is that if you do the low energy measurements, neutrinos are only stored. You don't invoke any other additional interactions. Low energy neutrino interaction is all stored. However, we believe the theory is valid at higher energies, and you introduce symmetry. The symmetry is our standard model symmetry. And very typical, the neutrinos will correlate and couple with the electrons. So charge currents will be even stronger, even neutral currents. Additional neutral currents will couple to both leptons and neutrinos due to iso2 symmetry, due to the standard model symmetry, if you want to apply to high energy. So that's the reason. That's the reason we are able to do both low energy and high energy. So from this, the plots, here is case 1 with the muon flavor. I remember I mentioned muon flavor dominant. Here is case 3 with the tau flavor dominant, and case 2 is tau and the muon share. So those are the signatures we want to search for at the LHC, but in comparison to the low energy measurements. So those are this situation with all mass parameters, wherever is acceptable. We come from a very low energy actually. So if the Z prime, the new state is significantly lower than the Z mass, and so turn out the dominant signatures will be the typical Julian Z production. And then you have additional light Z prime to radiate off the standard model formula here. So you are looking for 4 charge leptons, actually. So that's the dominant channel. However, if the Z prime is heavier than the Z particle, then Z prime is produced directly as a pair. So we have 2 classes of lepton signatures. One is a 4 charge lepton to form a Z prime resonance and a Z resonance. And the second class is simply lepton pair to form this one. We use both of these signatures to compare with the existing data. It so turned out that the other CMS have done a lot, including B factory, and as well as the B factory, both LHCb and BIO2, not BIO2, BIO experiment. They have both. So we recast these their measurements, and then we obtain some bounds, and we go beyond and to see the possible sensitivity or the prediction for the high luminosity ellipse, HL ellipse. So that's what we did. So then here is the summary plot, pretty busy, including everything I just described. So at the low energies, then the oscillation fit. So here is, for example, you see, this is case 1 with the muon flavor dominant, case A. This is case B with the muon and the tau mixed, and case C is the tau dominant. So that's the 3 cases here. Then all these plots here at the low energy region, those curves here is oscillation fit. It's line. The straight line here is current oscillation fit, and the lower line is more sensitive to include the projection from Dune and T2HK. So those are the ones. The coherence, the new measurement, comes from here, like this. At a very low energy, and so the oscillations seem to be a very low mass, so very low Z prime mass, and then the coherence becomes more and more important like this. So that's the situation. Now, if you go to a higher energy regime, collider clearly takes over. So those are the state region here are from the LHCb measurements at for the electron pair reconstruction. And here it's not very clear. This region is accessible by Barbar. So this is Barbar and B factory, the plus minus B factory here. There are a few holes. There's a few holes that is typically from upsilon to J psi, because it's a J psi upsilon, the peaks are so high that you don't have sensitivity to mu Z prime on top of that anymore. So there are a few holes. Otherwise, it kind of continue. Then we move on. So here is the atlas and the CMS recast. So then those are the 2 lower curves, our calculation for this particular model. So you can see the sensitivity, it can go all the way up to the accessible energy region, keV. You can even be able to go to almost like keV because of the LHC, the energy. But the G prime sensitivity is order 10 to the -3 in that level. So it's quite sensitive in that regard already. But the fun thing is complementarity. If this the new Z prime mass is around GeV below, it becomes very sensitive for the low energy neutrino oscillation measurements. But if the mass is heavier, and then the neutrino, low energy neutrino experiments certainly are not going to be sensitive enough, and you open the energy threshold and you go to the LHC. So that is a summary. To make a summary, just basically repeat, if the mass is around the MeV range, 20 MeV and below, and the neutrino oscillation experiments will be most sensitive. Future Dune and T2HK, T2 hybrid K will be dominant ones. But if you go further, heavier, then the oscillation will be not as sensitive as the coherent. Coherent is the one I mentioned at the Oak Ridge. Oscillation neutron source. And then if you go to the GeV region, then the collider takes over. So then you move on. This is the simplest possible consistent theory to give you the NSI, non-standard interaction, but the consistent possible, the renormalizable, of course, and then all the natures you need to apply to the high energy regime. So that's the basic example. We went through one more exercise. So we go through one more exercise to say that how can we even observe both? Okay, we pick up one particular example that here is a 10 GeV-ish signature for case A and case B. Suppose the LHC will have some sensitivity to this 10 GeV Z prime there already, and that will change the 4-lepton spectrum from the Z and there as well. Suppose this is almost like a 3 sigma signature or something. Let's go back to compare with the oscillation. We hope that somehow we can observe both, so that is very conclusive. These underlying dynamics seem to be at work. It's somewhat possible. So here, this is the region for this coupling and the mass, and this the red band is the possible sensitivity from this the future coherent experiments. It's possible. The certain parameter regions, not a lot, is that it's possible for both of them to have the sensitivity. Otherwise, one dominant the other. But sometimes it's possible. That's interesting. Okay, let me be quick for the 5 minutes. Oh, that's rather quick. So I have to be rather quick. So this is the other example. We know that we eventually want to understand the neutrino mass, and we know that the simplest formulation is this division 5 one-word operator. So then it gives you the spirit to the seesaw mechanism, right? So electric is a pivotal in between, and then the new Majorana mass will be the high mass end. So this is the. So then we have these the three simple tree-level mechanisms, the seesaw mechanism. So we should accommodate our colleagues sitting in the audience. Quite a few of them, Gorham and Xiaogang, and quite a few contributed to the mass generation formulas a lot. So type 1 is the typical situation you search for the heavy Majorana neutrino, let's say maybe several neutrino, from mixing from maybe even along with the W prime, as YE discussed in his talk. So type 2 is the difference. Type 2 is to introduce the no need for the right-hand neutrino. So type 2 has no right-hand neutrino in typical situation. You need to introduce the scalar triplet, Y equal 2 triplet to generate. So those are the neutrino mass term and copied to the Higgs. So there's a explicit lepton number violation by 2 units. Type 3 is to introduce the fermionic triplet. These are only 3 cases at tree level. And Xiaogang, of course, is famous to contribute this the type 3 class. So those are typical situations. We started this phenomenology and even LSE experiments going on to this will continue. But our question is, can we have a different interaction, different signature in connection with the low energy oscillation? So that's what we introduced the second case. We call this we introduced a new non-standard interaction and with a new scalar. This new scalar only coupled. In fact, this new scalar only coupled to neutrinos. This new scalar does not couple to the sharp leptons. It's a different. It's not as easy a signature as what we discussed previously. Previously, that's a Z prime. The Z prime coupled to both neutrinos and the sharp leptons. These ones are not coupled to the sharp leptons. I have no time to describe. There are possible UV completion for this kind of interaction. But it's kind of contrived. But so there are examples you can formulate these in the UV completion picture. But I will not do this UV completion picture. I only introduce this the scalar. I even don't need to introduce the lepton number violation. This scalar could carry lepton number 2 and to give you interaction. So this we want to search for. It so turns out that this scalar, if the scalar only coupled to neutrinos, this scalar will be radiated off for any neutrino, standard neutrinos. So therefore, where the neutrinos are from, W and Z. So anywhere you have W, Z in the standard model, you will have neutrinos from this lepton decay, and you will have this new particle radiated off. So that's why you search. That's why you search for these. So we will study the meson decays. We study meson decays, Z decays, W decays, and very similar to the dark force, like Wei just mentioned. But this one may even be just similar to the dark photon type of interaction. So it's come neutral, it's come everywhere. Kinematically it's different, but in terms of signature you can recast. So that's how we go through. So because of time, and this is the meson decay search. This is standard search going on for this pseudoscalar meson to charge lepton neutrino. We can search for the same thing because we have a charge lepton neutrino, and neutrino will radiate off this additional non-standard interaction. So it turns out this new interaction will change the neutrino oscillation behavior, change the coherence, it changes all the low energy neutrino interaction behavior because of this NSI. So we want to see whether we can do something along these lines at the colliders. And because of time, I would be quick. Here is from the dark matter type of search in the 64. And so many of these are similar to Wei discussed actually. So some of his search I think we must have used something similar. And from W decay, at the LFC energy, we produce W and W decay to these. You can even bound these from lab energy. Lab will produce large number of these and 2 neutrinos, and the lab neutrino will also radiate this one. So we put some bound here, and So this is document search bound, NA64. Okay. So this is a summary table. Because of the time, I would not go through this, but you can see we try to match as many available experimental data to the meson decays, having mesons all the way to B, and the tonic decays like tau decay, and the tubular decay, and Z3 invisible, and W from the LRC, and so on and so forth. Then we compared with this the fitting to the Mino measurements, the Dune measurements, and so on and so forth. So those are the range in different mass region and different coupling strength. So typically, we are able to probe the branching fraction for decays to 10 to the minus 5, 6. It's a coupling constant typically 10 to the minus 3. It's an interesting region already. It's not totally meaningless, so it's interesting. Now we combine we consider many other constraints, astronomical, cosmological, but I have no time to comment on. So let's just simply summarize. So this is the signature. Wherever the neutrino, there's a new radiation. This will turn out to be dominant channel. VBF, black boson fusion channel, is this dominant channel. So, and Christoph discussed the Higgs physics. VBF is important, and this one will have a very similar signature with the jet kinematics. And we studied the signature like this. I studied in comparison to the background. And we identified kinematical differences. The blue color is the signal for higher TT, the harder spectrum, and more back-to-back in the azimuthal angle and so on. We identify some VBF features. We implement the features, and here it's come to the summary conclusion. Okay. Once again, it's similar to the previous conclusion. At the low energies, all these low energy measurements will have sensitivity to this missing new particle already, but at high energy and the LRC, and luminous LRC will take over to have the sensitivity once this particle is a few GeV above overall. So that's basically the conclusion. So because of time, and I would just summarize what the studies have told us. It is interesting to look into these the non-standard neutrino interactions in a generic form. We want to see the bounds and the possible observation from neutrino oscillation measurements, but in the hope that these underlying dynamics will have different observational aspects. So we want to apply the same interactions to the collider energy, collider environment, see how the collider can coordinate with things. If we believe there is underlying dynamics, they must show up on both ends. So the first example is this the UV complete. Simply is the UV complete model for this non-standard interaction, and with the parameterized by Z prime. So those are the Z prime sensitivity. All the way up to multi-TeV due to LSE. All the way down to only MEV region. By the way, below MEV region, there are too much cosmological constraint. We did not consider the astronomical, cosmological, and a few the KEV region, that's a little bit too messy. We did not consider that. We consider a few MEV and above. Finally, second example is if the non-standard neutrino interaction is coming from a scalar, and this scalar even does not do much with the charge types, and this is the only example we come up. This scalar couples only to neutrinos. You can say they carry lambda number 2. It can be lambda number violation, but it's not important for us. We consider this carry lambda number 2, so that we compare with the current measurements and the bounds and prediction for the Dune, and then we go on to see the LSE bound. Once again, you can go to a few hundred GeV in that region. So we'll continue to think about this direction and try to make a connection in the neutrino sector for the non-standard interaction between the oscillation data and the possible correlation with the collider measurements. Thank you.
Questions? Okay, cool.
For the C prime model, would the lab can have some constraint when the E plus C minus hit the C prime pole with the initial state radiation?
Lab?
Yeah, right. Lab. I mean, you can have initial state radiation, the photon, and then E plus C minus hit right at the C prime energy. But of course, when the C prime mass is less than C mass.
We find the most sensitive bound is lab 1 at the Z mass. So this is one here. So this is the one that
I mean for the C prime model, the C prime.
yeah, C prime is this one. That's the most second one from Z decay. From the Z decay. From that is the Z, basically this process. The Z production at the somewhere. Z decay is one is most sensitive.
Maybe I can ask you a little bit.
Yeah, we can see some other also channels. Yeah.
Hello. Do you say the anomaly cancellation in your example?
Yeah.
Do you know why they cancel for such a simple choice? You just check it, or
Yeah. So this,
usually
yeah.
it is very complicated.
This yeah.
Do you know why they cancel?
It exists in the literature, so we looked into this. It's generic formula. We wrote down the generic formula for the cancellation. This is the formula for the cancellation. This is general formula for the anomaly cancellation for this D prime. This is typically B minus L type, very similar to B minus L type D prime. Most general situation is that.
Oh. Yeah, it is B minus L distributed among the leptons.
Yeah.
Okay.
Then we choose particular particular relations. We choose the charge lepton like this and quarks.
So if you assume 1/3 for the baryon, you have general parameterization to distribute. You have more choices than what you show. You can distribute the lepton number.
Generation wise.
Yeah. Okay.
This not the cancellation is more general. The choice is not.
Right.
The choice is, of course, we want to see the muon tau mu tau. We this assumption not to include the electron.
What I mean is you can put some alpha parameter to interpolate all these three. You can have a simple formula for 3 cases with the alpha parameter to distribute the numbers.
I see what you mean. That's a little bit more general. Yeah. So I think this can be done if you compare with the data. Just one more parameter, and yeah, I see what you mean.
Yeah, for the 4-lepton surge at the LHCb, is that come from the prompt lepton, a prompt signal, or if you consider displaced vertex, can the limit go down to 1 GeV? Page 12.
I don't think we get this the prompt the displaced vertices. This from the prompt decays from the four lepton surges. So this simply read off from the data. They have data. They search for the 4 leptons, both from the lab, so both from B factory and also from LSB. LSB has 4 lepton search too. We use their current experimental bound to the. We did not do the secondary vertex at all. I don't know whether the data exists for that. We just took the simple data.
I think we should switch to the next speaker. So there's a second hand again. Yeah.
Thank you.